what we're looking at in Chapter 4 culminates in another application of calculus, which is optimization problems or max-min problems. So we're going to start off today by looking at something called increasing and decreasing functions, and our primary goal here is to use the derivative of a function to determine where functions are increasing and where they are decreasing. And the fundamental idea behind how this is going to work is pretty basic, but it's something that we have to keep coming back to throughout this chapter and also the next chapter. So what we're going to be investigating here is where functions have values that increase over x. I'm going to explain what that means, or values that decrease over x. So first of all, the word function is another way of saying y. So when I say a function has values that increase, I'm saying y is increasing. And when I say over x, that's an important idea, that we're always looking at behavior from left to right graphically. So over x means as x increases, what happens to y? And I think it's pretty obvious, we're going to formalize this in a second, but if y is increasing as x goes up, then you have a positive slope. The graph is climbing. If it were a graph of money as a function of time, the amount of money would be increasing. That's an increasing function. Whereas if you looked at the value of a new car once you buy it, and you plotted the value of the car on the y-axis, the value of the car would be decreasing over time, over x. There's lots of ways, really complicated ways to define where functions are increasing or where functions are decreasing, but the most efficient, I find, way to do it is to look at the derivative. And this is what I talked about at the beginning, maybe before I started the recording, by saying the fundamental idea behind what's going on in this lesson is really basic, but it's something you have to think about and understand. If the derivative of a function has a value that's positive, when I say greater than 0, I mean it's positive. If I tell you in a certain region on a graph the derivative is positive, I'm telling you the function is increasing. And think about this for a second. I'm going to go away from graphs and functions and start talking about things that maybe you're more familiar with right now because we've spent so much time on related rates. If I tell you that in a particular situation, d shadow dt is greater than 0, what I'm telling you is the derivative of shadow length with respect to time is positive. What that means is the shadow is growing. I mean, fundamentally, this is what differential calculus is all about. You understanding that this operation is telling you what's happening to the thing you're operating on. So if d shadow dt is greater than 0, if it's positive, that means the shadow is increasing over time. If I gave you a situation where I had d volume of a snowball dt and it happens to be a negative number, what that means is that the volume, I guess it doesn't even have to be a snowball, but we've done problems with snowballs. The volume is decreasing. So this is the main idea. If you look at what's at the top of the screen, if the derivative of a function is positive somewhere, then the function is increasing, and if the function is increasing, it has a positive slope. I mean, we can translate this to my first illustration here with the shadow. If I plotted shadow as a function of time, if the shadow length is increasing or if the shadow is growing, the graph might look like that. That's a positive slope. If I were to look at this second illustration that I came up with off the cuff, and I said dv dt is negative, that means the volume is decreasing, what the graph might look like is that. And by the way, everything I'm talking about here at this point in time is something that, you know, as a calculus teacher, my hope is this is obvious to you. This is what we've been spending the last 6, 7 weeks talking about, is rates of change. Maybe not 7 weeks. On the other hand, wherever the derivative of the function is negative, that would mean the function itself is decreasing, and that would mean there's a negative slope. The slope is in a negative direction. So we're going to do a warm-up here just to kind of gel these ideas. What I have is a polynomial function. It's a degree 3 polynomial function. And you're given some information. There's a maximum at 1 and there's a minimum at -3. There's a couple of words here that are maybe unfamiliar to you. I may have mentioned them in my Math 30 class. It's the word local. We're going to talk about that in more detail, greater detail tomorrow. But all the word local means, everybody, I can talk a little bit about it right now, is if this is a local maximum here, that means that it's a maximum value of the function, which is y. It's a maximum value of y in that area, in that local area. Because clearly you can see that since this graph goes up over here, there are going to be values of y larger than that value of y at x equals 1. That's why it's called a local maximum and a local minimum. So all I'm telling you is it reaches a peak at x equals 1 and it reaches a valley at x equals -3. And the first question of the warm-up says, what is the domain in which the polynomial function is increasing? Well, the polynomial function would be increasing wherever the polynomial function has a positive slope. And the positive slope occurs everywhere between here, everywhere between here and here. So, and you can choose to include this on your diagram or not. I have a couple of different ways we can draw it. But the point is, the function is climbing left to right. The function is going up everywhere between -3 and +1. So we would say that y is increasing over the interval from -3, the interval from -3 to 1, not including -3 and not including 1. And to explain why it's not increasing at -3 and why it's not increasing at 1, I think requires us to step into the realm of calculus and derivatives. The reason why y is increasing over that interval is because dy dx is greater than 0 over that interval. If I asked you what dy dx was at, say, 1, I hope you can come up with the answer. Who can tell me what the value of the derivative of this function is? It's p of x, so I'm going to write this p prime of 1. This isn't part of our answer to this question. This is just me explaining something. What is the value of the derivative of this function at 1? And I really don't like this prime notation, so I'm going to say d dx of p of x at x equals 1. What is the value of the derivative at x equals 1? It's 0, exactly, because the slope of the tangent is 0. It's not, the tangent isn't pointing up at x equals 1. It's not pointing down. It's horizontal. So that's why we can put dy dx is greater than 0 over that interval, but that interval cannot include -3 or 1. If I said to you, where, and you can choose to add stuff to your diagram, to your graph, if it helps your explanation or it helps your understanding, but where is the function decreasing? Well, the function is decreasing everywhere after 1. Everywhere after 1, the function is decreasing. It's also decreasing everywhere before -3. And it always, it's interesting because when you look at that arrow on the left-hand side, we tend to fixate on that arrow on the left-hand side and go, oh, it's going up. But remember, when we talk about the function, we're talking about from left to right. So when you go from left to right on the portion on the left side of this graph that I've highlighted in green, from left to right, the graph is going down. So we could say y is decreasing. I want to check something, make sure I wrote the right word. I did. Y is decreasing on x is less than -3 and x is greater than 1. And I used the word on this time instead of over, just to illustrate to you that we have different words we can use here. It isn't that we use the word on when we're talking about decreasing. It's just a different word than over. Over the domain, on the domain, within the domain. And what we could put here is that dy dx is negative on x is greater than 1 and x is less than -3. So again, left to right, this is what we're talking about. Left to right, the graph is going down here, the graph is going down here. Always left to right. Left to right, now you only have one graph, but left to right here, the graph is going up. The third part of the warm-up says determine the domain in which the polynomial is neither increasing nor decreasing. Well, there's only three possibilities for the value of something. It can be positive, which we talked about in warm-up part 1. It can be negative, and that's what we talked about in warm-up part 2, or it can be 0. So what we're talking about here is where the derivative equals 0. And the derivative equals 0 at x equals -3 and x equals 1. So it's not, y is not changing. It's not increasing and it's not decreasing at x equals -3 and x equals +1. Graphically, that can be represented by this. So what I have, if I put this all together, is 1, the answer to number 1 was this. The answer to number 2 was this. And the answer to number 3 are those two brown points. We run into this problem, and it's been a few weeks since we've talked about it, that the word, think about this, the word increasing, that's over time, right? The word increasing implies a change from one place to another. And that makes perfect sense when you look at the red portion of the graph. I'm just going to go over to here and look at the red portion. It's going from one place to another, so the word increasing applies. When you look at the green portions of my graph, this is where it's decreasing, where y is decreasing from one value of x to another. Be very careful here in trying to wrap your head around what it means to say that it's not changing at a point. That point, in terms of x, has an infinitely small x. The word change cannot apply to a single point. You've frozen time at that instant. It goes back to the idea that just because my instantaneous speed happens to be 85 kilometers per hour doesn't mean that's how fast I'm driving all the time. Or it doesn't mean that I'm driving that fast for an hour. That's just how fast I am at that instant. All right, we could put this another way, and I don't know if this is going to help or not. I've never done this before at this stage, but what you could do is you could say that at this point and this point, dy dx equals 0. We're going to be doing kind of representations in this form later on, and I thought I would just throw it in here. In this region, dy dx is positive, and in this region and this region, dy dx is negative. This is maybe a little bit easier for you to wrap your head around, at least when you're looking in your notes, because by the time you put all of those different colors on the graph, unless you have different colors, all you've done is you've just filled in the graph. My mistake. Thank you, Evan, for the furrowed brow. Less than 0 there as well. Is that better? Okay. I mean, I like these line graphs. I think line graphs are very communicative in terms of giving you information. So again, we're talking about where y is going up or going down or not changing in terms of x. And we're going to do 4 examples now where we find out the intervals of increase and decrease without looking at a graph. We look at the calculus of the situation. So to begin with, we're going to be working on what's called a first derivative chart. Now, it turns out you've done a first derivative chart. Remember that somewhat nightmarish lesson dealing with position, velocity, and acceleration? And I say that because it always is. It's a difficult thing to wrap your head around. By the time we get to the end where you're trying to find distance traveled, that's horrible to really think about. But one of the reasons why I include that, and it is elective material in this course, it's optional, I don't have to teach it to you. One of the reasons I include it is we've done charts in that lesson that are the same as first derivative charts. So let me show you what I mean. The first example says, where are the intervals of increase and decrease for each function? So the first thing we want to do is we want to find the derivative of the function. I'll use f prime of x. I differentiate this function and I have negative 5 minus 14x. And this is something I've talked with my Math 20-1 students about, for those of you that were in my Math 20-1 classes. If you want to find out where f prime of x is positive, because that's where the function increases, and you want to find out where f prime of x is negative, because that's where the function decreases, then you have to first find out where it's equal to 0. Because this function, everybody, is a polynomial function, it's defined from negative infinity to infinity. So it is a sure bet, 100% guarantee, that somewhere in that interval the derivative could be 0, somewhere it could be positive, and somewhere it could be negative. But the important thing is, when you look at all of those domains, they all have to be everything from negative infinity to infinity, because this function exists everywhere. So I'm going to start off by asking myself this question. Where is f prime of x equal to 0? And this is just the thought that's going on in my head. You may not think what I'm about to tell you is important, but I think it is. We are not going to write out the derivative equals 0. We're not going to put negative 5 minus 14x equals 0. This is what I believe is important. We're simply going to express the derivative in factored form. And in this particular case, there's nothing to factor, is it? You simply have to look at that and decide what value of x would make it 0. Now, I have to admit that in order for you to do this, you're going to imagine it being equal to 0 and you're going to rearrange it. But for a reason that maybe isn't that important today, but it's going to be crucial in the next chapter, as soon as you start doing this, you run the risk of introducing errors in your work. Okay? We just don't want to do that. And I'd rather not explain what those errors are until we have to encounter them. So all I'm doing is I'm imagining that's equal to 0, and I say that the value of x of 5 over 14 being negative makes the derivative 0. And look, I don't want to lose anybody because I'm not writing equals 0. If you want to write equals 0 down and rearrange that equation, fine. But later on, I'm going to kind of scold you and say, stop doing that because it causes problems. Okay. This value of x is what we call a critical value of x. It's a critical value of x because it makes the derivative 0. There are other reasons why a value of x could be critical, and we will talk about those tomorrow. But what I want you to note right now is this, and we can't run away from the logic here. You need to understand this. If the derivative is 0, then the value of x that makes the derivative of 0 is called a critical value of x. But just because you have a critical value of x doesn't mean it makes the derivative 0. Which means that critical values of x can happen because they make the derivative 0 or because of a different reason. Okay. So what does this mean? It means, and I really don't know that this number line is important. This function, well, I don't think it's important in what you write down. I think it's important in what it's telling you. This function exists from negative infinity to positive infinity. And we know that at negative 5/14ths rather, the derivative is equal to 0. And I want to spend some time talking about the logic of what we're about to do. First of all, resist the urge to think of this graph and what it looks like, okay? Because I know we can answer it quite easily by looking at the function, but that won't always be the case. So, let me just move something. If x equals negative 5/14 is the only place from negative infinity to infinity where this thing is equal to 0, where the derivative is equal to 0, and the function exists everywhere, that means the function to the left of this must be positive everywhere or negative everywhere. And to the right, it must be positive everywhere to the right or negative everywhere to the right. It cannot be over to the right, positive in some place and then negative in another place, because then it would have to pass through 0 again. So, how are we going to actually answer this question? We are going to make a first derivative chart. The first derivative chart will contain intervals along the side that are created by taking slices of the infinite domain wherever there's a critical value of x. So I want to investigate the function from negative infinity to negative 5/14. I want to investigate the function from negative 5/14 to positive infinity. And by the way, when I say investigate the function, I'm talking about investigating the derivative of the function because it will tell me about the function. Across the top, I'm going to put all of the factors of my derivative. Now, there's only one factor here, which actually makes this problem of the 4 more complicated to understand what's going on, because there's only one factor, so it seems like the chart is not necessary. And what you're going to do, what I'm going to ask you to do, everybody, is choose a number for x that's in this first interval, this interval that I'm pointing at right here. Choose any number for x that you want and put it into that factor negative 5 minus 14x and see what you get. It will either be positive or it will be a negative. How many of you see the nature of it, whether it's positive or negative, just based on the numbers without actually loading in a number? It's going to be positive. If I put in a number like negative 100, then I'm going to have negative 5 minus 14 times a large negative number, so it will become plus a large positive number. If I do the same thing here, I get negative. Now, how many of you remember when we did this with velocity and acceleration, that I made a big deal in the table of saying it goes from negative to positive. It goes from negative to positive. Do you remember the exception to that? Do you remember, Evan? Because this doesn't go from negative to positive.
When it touches.
You're thinking of the graph, though, right? And that would be the case. It could be negative, negative. It could be both. And by the way, don't forget that what we're talking about here is not the parabola. We're talking about the derivative of the parabola. The exception was if the coefficient of x was negative. When you have a linear factor, it will go from negative to positive past the zero unless the coefficient of x is negative. So I'm going to come back to that in a bit. What does this tell us? It tells us that dy dx is positive in this interval and negative in this interval. And I'll be the first to admit, I don't really believe we needed a table to figure that out in this case. What that means, and this is what will be important now, is that y in this interval is increasing. That's how I communicate that statement. Like, look at those last two columns. One of the columns is telling me about dy dx. It's positive. The other column is telling me about y. Y could be positive or negative. I don't know. But since dy dx is positive, whatever y is, it's climbing. It's going up, which is why we draw that arrow. Whereas if dy dx is negative, the function is decreasing. So this is an interval of increase whereas this is an interval of decrease. And again, this is a fairly basic one because we only have two intervals, because there was only one critical value of x. So you take that domain, you slice it once where that critical value of x is, you have two intervals to explore. Any questions with that first example? Go ahead. Of course. All right, let's take a look at the next one. So we have a degree 3 polynomial function. Again, I think it's worthwhile for us to understand that this function, since it's polynomial, exists everywhere. So the domain of this is negative infinity to infinity, which means when we build our first derivative table, we have to start at negative infinity and end at positive infinity. It has to include every value of x. Let's find the derivative. I'm going to use Leibniz's notation this time. I think it's Leibniz's. ds dt is equal to 3t squared minus 24t plus 36. And now, finally, what are we always supposed to do with derivatives? Factor them. This is why we're factoring them, so we can put the separate factors into a derivative table. I can take a 3 out of this and be left with t squared minus 8t plus 12. And this factors further into 3 times t minus 6 times t minus 2. What does that mean? It means we have two critical values of x, 2 and 6. Again, I don't know that you need to draw this number line, but what we know is that at x equals 2 and at x equals 6, the derivative is 0, which means everywhere else it's not. Everywhere else it's either positive or negative, depending on the derivative. So we are going to slice it here and here in terms of the entire domain and look at negative infinity to 2, 2 to 6, 6 to infinity. And that's what we build our chart based on. put your intervals in numerical order. If you don't, it gets very confusing. So don't draw this, but what I mean by that is we are going from negative infinity to 2, then we're going from 2 to 6, then we're going from 6 to infinity. They're listed in the order from negative infinity to infinity. Across the top, we put all of the factors of the derivative, which means we put the 3, the t minus 6, and the t minus 2. Yeah, why do we need to put the 3? I think if you ask that question, that tells me that you understand the purpose of this. The 3 is going to be positive everywhere because 3 is 3. It's a positive number. But I want you to get in the habit of putting it there because if that constant you factor out happens to be negative, that plays a role in the derivative. And maybe right now, I will explain right now why you really should stay away from writing equals 0. Because there's a temptation to do the following. If you had negative t squared plus 8t minus 12, and that's your derivative, I guess it's dy dt, and that's your derivative, then you know you have to factor that, right? You've been taught in Math 20 that you need to zero the equation, and probably your teacher, myself included, would say, let's move everything to the other side, where the quadratic term becomes positive. But if you do that, it's no longer the derivative, it's the negative of the derivative. Right? If you just go, oh, you know what, I'm going to do this to make my life easier. I'm going to change that to a positive, and that to a negative, and that to a positive. This isn't the derivative anymore. So if you write it equal to 0, you might run the risk of getting things backwards. If that kind of went over your head, I wouldn't worry too much about it. Just remember, don't set it equal to 0. All right, so those are our factors. I'm going to include as well a new column for I guess it's ds dt. And I'm going to include a final column of s. So positive, positive, positive. If you don't want to include the 3 in this example, that's fine. If you want to group the 3 with the t minus 2, that's fine. The t minus 6, by the way, the order of the top factors doesn't matter, will be negative, negative, then positive. You can put numbers in, but 6 happens here. This is where t equals 6. So before t equals 6, t minus 6 will be negative. T equals 6 is where t minus 6 flips from negative to positive. Using that same logic, this would be negative, and then it immediately switches to positive. And then we multiply these together. Positive times negative is positive. The derivative is positive in this interval. Positive times positive, it's negative here. And then 3 positives multiplied is positive. What does that tell us? It tells us that s is increasing in these two intervals, and s is decreasing in this interval. So s is increasing on negative infinity, comma 2 in union with 6, comma infinity. I don't care the format that you write it out. You could write it in words if you like. Just don't write a poem about what the answer is. I want some kind of meaningful mathematical statement. And s is decreasing on the middle interval, which is 2 to 6. And again, I probably don't need to say this, but you never know. These are not xy coordinates, right? They are x values, minimum and maximum x's. ask you a question here. How many of you can tell me what has to be here if the function goes from increasing to decreasing? The function is defined everywhere, and prior to 2, the graph is climbing. After 2, the graph is falling. What's at 2? There's a maximum. This is how we find maxima and minima. And you just learned how to find the maximum, the coordinates of the maximum of a cubic polynomial function. All right, let's try a couple more. C. Let's try a degree 4. So g prime of x, I'm going to use dy dx. dy dx is equal to 4x cubed minus 12x squared minus 16x. I always want to work that towards a factored expression. I can take out a 4x and be left with x squared minus 3x minus 4. I can factor that further into dy dx equals 4x times x minus 4 times x plus 1. Some basic quadratic factoring there. Negative 4 and 1 multiply to give negative 4 and add to give negative 3. Our critical values of x will be negative 1, 0, and 4. And really, what it boils down to, there's bound to be exceptions here, people. But what it boils down to is when you're solving this, when you're saying it's equal to 0 and you're solving that equation, all you're doing is looking at all of the factors. You're looking at the factor of 4x and saying, how can 4x be 0? Well, when x is 0. So if x is 0, the derivative is 0, which means x equals 0 is critical. Something is happening there. How can the x minus 4 be 0? Well, if x is 4, so 4 is another critical value of x. And I can see that many of you are already on your way to constructing the table. Across the top, you're going to have 4x. I'm going to include the 4 with the x. I think writing a separate column for 4 and a separate column for x is probably overkill. If you want to, you can. I'm going to need an x minus 4. I'm going to need an x plus 1. I'm going to have a column telling me what they tell me about dy dx and what dy dx tells me about y. We're going to be going from negative infinity to negative 1, from negative 1 to 0, from 0 to 4, and from 4 to infinity. Again, everybody, generally speaking, and things are going to ramp up tomorrow. These are all polynomials so far. It'll actually ramp up in D, but tomorrow we'll be looking at more complicated functions and more complicated situations. But again, I hope you see, since there are 3 critical values of x, you make the slice of the infinite domain, negative infinity to infinity, you make 3 slices. You get 4 chunks. I would like everybody to populate this table with positives and negatives, up to but not including dy dx, or you can do that, I guess, if you want. But I just want you to do it on your own. By a show of hands or a nod of the head, how many of you see what a time saver it is to just recognize that negative turning into positive past the 0? So I want to go through that one more time. When you look at the factor of 4x, the 0 for that factor is right here. It's at 0. So before that, that factor is negative, 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 and then it becomes positive. When you take a look at the factor of x minus 4, the 0 for that factor is 4, which occurs here. So before that, that factor is negative, and afterwards it becomes positive. When you look at the factor of x plus 1, the 0 for that occurs at negative 1, which means before negative 1 that factor is 0 and afterwards it's positive. The only reason that works is because these are positive x's. Okay? So if you have a negative x, then it's backwards. The reason for that is a positive x is a positive slope, so that's as a line, it goes up across the x-axis. All right, so what is dy dx? dy dx, negative times negative times negative is negative. I like to circle the dy dx's to separate them from the other stuff. Then negative times negative is positive, times another positive is positive. This one is negative, and this one is positive. So y is decreasing, then increasing, then decreasing, then increasing. I guess we have to formally answer the question. I want to go and take a look at the notation. It was g of x, so I guess I can use g of x. G of x is increasing on negative 1 comma 0 and on 4 comma infinity, and it's decreasing or is it decreasing negative infinity comma negative 1? And I'm not using the union symbol. I guess I could, but I decided not to for some reason. And 0 to 4. And these are all round brackets because we don't want to include the square brackets, because the square brackets would include the critical values of x, which is where the function is not increasing or decreasing. It has a derivative equal to 0. Any questions with C? All right, if we take a look at D, D is decidedly different because it's not a polynomial function. So the first thing we need to do is find the derivative of this. I'll rewrite it. Y is equal to x times 9 minus x to the half. We have to use the product rule. So we have to rewrite it with an exponent, and then we have to use the product rule. So dy dx is equal to the derivative of the first times the second over, my mistake, plus the first, which is x, multiplied by the derivative of the second, which is 1/2 times 9 minus x raised to the negative half times negative 1. And I would like everybody to just soak that in. Just look at that for a second and make sure that you understand why I've written what I've written. I think the first part of this is fairly straightforward. The derivative of x is 1 times the second part. And then we have plus the first, which is x. And I wrap that half around the 9 minus x, which stays the same. I drop 1 from the exponent. The exponent becomes negative 1/2. I multiply by the derivative of what's inside. I'm going to choose, everybody, to recommend to you that what we do is we write this over 1, because I would like to eliminate that fraction of 1/2. I don't want to deal with a fraction of 1/2 in one term when I don't have fractions in the other term. So there's two things I need to do. The first thing that I'm going to do is multiply the top and the bottom by 2 to get rid of that half. So I get dy dx is equal to, I'm going to have 2 times 9 minus x raised to the half, plus, well, actually minus, because of that negative 1, I will have minus x times 9 minus x to the negative half, and this is over 2. You can, if you like, well, I mean, you should be doing this anyway. Just double checking what's happening here. I'm multiplying this 2 by that term, and I'm multiplying the 2 by this term, but when I multiply the 2 by the second term, the halves cancel. Are we okay with what I've written there? Okay. The second thing, I said we have to do two things. The second thing is we can't have negative exponents. Now, I told you that critical values of x are the values of x that make the derivative 0. It's not necessarily clear what all those values of x are unless you factor it. I'm going to tell you in a minute what the other condition for a critical value of x is. Do you remember me saying if the derivative equals 0, that's critical, but there's another reason? We'll get to that. So I'm going to factor out the negative exponent. What I mean by that is I'm going to factor out the base raised to the lowest exponent, which will be 9 minus x to the negative half. And then I'm going to have left 2 times 9 minus x to the 1. And I'll ask you to soak that in as well. Why do I have left 9 minus x to the 1 when I take 9 minus x to the negative half out of 9 minus x to the positive half? It's because the exponent that I put here has to be what I add to the exponent I take out to get the exponent I started off with. And man, we've factored out an exponent of negative half out of an exponent of a half 100 times. Okay. Let me get rid of these arrows. They're just going to distract me. Then we have minus, I guess just minus x. And this is over 2. Now I can simplify it, and I have dy dx is equal to, on the top I have 18 minus 2x minus x. On the bottom I have 2 times 9 minus x to the half. So I've expanded that interior part of this by multiplying that 2 through. So the 2 times the 9 is the 18, and the 2 times the negative x is negative 2x. Just a little bit further to go with this. I'm sorry, I will pause there. Are we okay to that point? And I guess I'm not, that's a rhetorical question. I'm not asking, are you okay with it? I'm asking you to just think about it and see that you're okay with it in your own head. I can simplify the top now into 18 minus 3x over 2 times 9 minus x to the half, quantity to the half. I know I like to work top to bottom, but I'm just going to move this over here. I can take out a 3 and have 6 minus x over 2 times 9 minus x. So this is dy dx. So what are the critical values of x? What are the values of x that make the derivative 0? Well, a fraction, and that's what this is 0 if the numerator is 0. Okay? So if x equals 6, that makes the derivative equal to 0. And what happens when the derivative is equal to 0 is that, this is really why it's called critical, and this is where we're going, is that it could be a place, but may not be a place. It could be a place where there's a max or a min. Because if the derivative is 0, then the function could be going up, increasing, and then going down, in which case it's a maximum. It could be. But there is also a critical value of x of 9. And I'm telling you now, and this will be formalized in your lesson tomorrow, that a critical value of x is any value of x that makes the derivative either equal to 0 or undefined. Now, I could have saved this example till tomorrow and then done it all with everything tomorrow. I've discovered over the years, I want to introduce it now. A critical value of x makes the derivative 0 or undefined. I'll come back to that if we have time. Okay. So we have two critical values of x. Now there is something different here. And if I were to write this, don't write it please. If I were to write this, that I'm going to take the domain of all real numbers and make a slice at 6 and a slice at 9 and use those three intervals, I would be wrong. Why is what I've written in green not a logical description of what's happening with this function? Liam. Right. The domain is not every real number. This has a radical. So with the first three examples, they were polynomial. And I just wanted you to get used to the fact that we're slicing up a regular domain using critical values of x. But this function, and I'm going to go to a new page just where I can clear my head. This function was y equals x times root 9 minus x. Now, you may have not be technically correct. I think we have to include 0 as well. Like you said, x is greater than 9 or something. But let's walk through that. This function has a radical, and for any radical, there is something called a radicand, and the definition of a radical only exists if it's a square root whenever the radicand is greater than or equal to 0. The radicand can be 0 because you can take the square root of 0. The radicand cannot be negative because you cannot take the square root of negative. It can be positive or 0. So what we're going to do here is this is our domain exploration. What's the domain of this? We're going to write 9 minus x is greater than or equal to 0. And we have to solve this. And this little bit of business is a grade 9 thing that high school students screw up on all the time. It's a slippery thing. I hope that everybody gets it. I hope that you understand the domain here is x is less than or equal to 9. But I can easily see why students would get it backwards. Because what some students might do, and this is really important, is you might subtract 9 from both sides and get negative x is greater than or equal to negative 9. And then you go, oh, well, I'm going to divide both sides by negative. Or I'm going to multiply both sides by negative. And get an x here and a 9 there. But the little seldom remembered rule with an inequality is when you multiply an inequality by a negative or you divide the inequality by a negative, you take the sign and you flip it. You have to flip this over. And by the way, this is not how I would have done this question. Most of you have had me as a teacher last year and in Math 30, and even if you haven't, you've had me for a few weeks now. I hope you know that I'm a fan of finding variables and arranging equations so they become positive. What do I mean by that? That was really awkwardly put. I would rewrite this way. I don't like having to deal with negative x's. But then I read it backwards. And I'm going to put this into symbolic form. What this is saying is 1, 2, 3, 4, 5, 6, 7, 8, 9 is greater than or equal to x. Well, if I take that and I read it backwards, that means I have to flip this. I have to look at it in a mirror. And that's what it looks like in a mirror. It has x is less than or equal to 9. I know that I've maybe in some of your minds wasted 5 minutes of our time talking about solving this inequality right here. But it's important. It's such a tiny little mathematical idea, but it's important. So that means, everybody, x is less than or equal to 9 is the domain. Our domain is from here to the left, or negative infinity to 9. We are going to slice that domain at 6. We can't slice it at 9 because that's the end of the domain. So we really have only two intervals. We have negative infinity to negative 6, to positive 6, and then we have 6 to 9. And that's it. That's as far as we can go. Across the top, this is going to get interesting. We are going to put, there's my derivative here in the top right corner. I'm going to put the 3 and the 6 minus x together of a thing. I'm going to put these two together as one thing, one factor. And I'm going to put right next to it 2 times 9 minus x to the half. And some of you might go, and I get it, oh, but Mr. Way, the derivative is that first thing over the second thing, not times. But when I multiply two negatives, it's the same as dividing two negatives. It doesn't matter how I write it. If you want, you could put a slash there, although I've never seen it. You just simply put all of the factors. Another reason why the derivative needs to be factored. This will be, and let's put our dy dx. And let's put our y. This will be positive then negative. It's backwards because of the negative x. Don't forget, you can always populate that 6 minus x with any number you want in that interval. So 6 minus negative 1,000,000 is going to be positive. This is always positive simply by virtue of the fact that the exponent of a half means take the principal square root. And some of you might say, well, maybe it's negative somewhere. No, it isn't, because we've already said 9 minus x must be greater than or equal to 0. Somebody could then say, well, maybe it's equal to 0 somewhere. Yeah, it is at 9, but 9 is not in this interval. What do we get here? Let me move my dy dx up a bit so I have room. My dy dx is positive. My dy dx is negative. So the function is increasing, then decreasing. It's increasing on this interval and decreasing on this interval. All right. So any questions with number 1D? I want to explain something to you now. There's so many things we're going to be learning over the next few days that are all connected. And many of you will look at tomorrow's lesson and go, didn't we do this already? Some of you will look at Thursday's lesson and go, I thought we did this already. There's a lot of overlap. Let me graph this function for you. Actually, before I do, what we will officially learn tomorrow is this. A critical value of x is a value of x that we are suspicious might be the location of a max or min. And this is where the derivative equals 0 or the derivative is undefined, right? Let me graph this function. And I put some thought into why I'm using this function. This is going to kind of tie this whole thing together. I guess I could have just used square root, but I'll raise it to the 0.5. I'm going to go zoom standard. I may play around with the window settings in a second. That's what it looks like. Okay, so I'm going to play around with the window settings. Let's go from negative 2 to, let's go 12, and we certainly don't need that. Negative 3 to 15. And I don't know if you remember this, everybody, but in Math 30-1, when we graph logarithmic functions, I made a point of saying where functions get very steep, your graphing calculator kind of has a conniption fit. It doesn't know what to do. And it's having a really hard time plotting the points in this region here. But I will tell you right now that what the graph looks like is this. You with me? This is where x equals 6. Would you agree that's a maximum? A maximum happens to occur at the critical value of x. Can you answer this question for me? On that graph, is there any other point that's a max or a min? There is. This is a max. This is a min. It's not an absolute min, but in that region, that's the lowest point, right? What's the derivative at that point? Want to take a stab? It's a difficult question. It is undefined. The reason the derivative is undefined is the derivative is a limit, really, of h approaching 0 of f of x plus h minus f of x all over h. It's a limit. But a limit only exists if the left and the right-hand limits are equal, and there isn't even a right-hand limit to talk about because the function doesn't exist. So here, this is critical because the derivative equals 0. The slope is 0. This is critical because the derivative is not defined, because it's where the function ends or starts, depending on how you look at it. So we're going to, tie this all together even more tomorrow. In the meantime, what you're doing is you are understanding what an interval of increase or decrease looks like on a graph, and given the equation of the function, you can find the derivative and do a first derivative table to answer the question. Question 2 are all polynomial. Question 3 are polynomial, but maybe a little bit more awkward to deal with. And question 4, you start to get into some more complicated things. You clearly cannot do all of these. I would recommend doing a couple polynomial ones. Maybe if you're up for it, something like this. Those are good ones to practice.